Okay, great. Thanks, Guchuan. Yeah, let me again repeat what Guchuan mentioned about the problem sessions. We just met for an hour and talked about the problems from the first lecture. And then on Thursday, we'll meet to discuss the problems from the second lecture, and then next Tuesday, problems from the third lecture. And we had a lively discussion. We clarified some details a little more informally, and everyone is welcome. Especially if you've spent some time looking at the problems. But even if you haven't, you're still welcome to participate in those problem sessions. Okay. All right, so the first thing that I want to do today is finish up something that we didn't quite get to last time. Last time, we spent the whole hour talking about Massey products. So Massey products are this deeper structure in ext groups that you can use to there's a richer structure in X, and we talked about how May differentials and how you can use Massey products in order to compute May differentials, and you can use May differentials in order to compute Massey products, and so forth. So the way one reason that you need Massey products is because they help you analyze ext itself, the atom's E2 page itself. Okay, so that's the background. That's what we did. The Massey products are useful for studying ext. That's the point. Okay, now it turns out that the stable homotopy ring has brackets as well. And usually when we talk in the context of a stable homotopy groups, we usually call them total brackets rather than Massey products. Although if you take the right categorical frame, probably triangulated category framework or something, total brackets and Massey products are really the same thing. But it's more context. We use Massey products in an algebraic situation, and I use total brackets in a homotopical situation, but they're not really any different. It's just context. Okay, so the total brackets are another example of this rich additional structure that we've been talking about throughout this mini course. That we're not just looking at abelian groups when we talk about stable homotopy groups. There's this filtration that we like to keep track of. And there's these higher brackets, these higher products, these total brackets, okay? And one of the things that I could have really said this in the first lecture as well, but the name, we talk about the stable homotopy ring, pi star, it's the stable homotopy ring. And I really dislike that name, the stable homotopy ring. Stable homotopy ring, it tells you, you should be understanding these abelian groups, and you should be understanding their product structure. That's what the word ring is, right? It means add, addition, and multiplication. And it's really, as I say, it's really an injustice to the rich additional structure that the stable homotopy object has. It goes so far beyond the primary product structure, okay? All right, so how you can, so it turns out that the Moss convergence theorem is a great way to get your hands on total brackets in the stable homotopy ring. Okay, so what it says, and again, this is just kind of a rough description, as we've talked about before, there are some technical conditions that have to be satisfied. They're not always satisfied, but they will always be satisfied in the examples that we're going to that we have discussed and that we will discuss in this mini course. Okay, so we can kind of ignore those technical conditions for now. So what it says, suppose you have a Massey product in ext. Okay, that Massey product in ext ends up corresponding to a total bracket in the stable homotopy ring. Okay, so there's really two parts to the Moss convergence theorem, and they're kind of different, and their proofs are kind of different. One, it says Massey products in ext. The other part of the Moss convergence theorem is about Massey products in H of ER. So remember how this goes. The E2 page is ext, it has Massey products. The E3 page is the homology of E2. E3 is the homology of a differential graded algebra. And so it has its own Massey products that don't really correspond to the Massey products from ext. And E4 is the homology of E3. E4 is the homology of a DGA, so E4 has its own Massey products. Okay? So you could have Massey products in ext that give you total brackets, or you could have Massey products in one of these higher ER pages, and those also those Massey products also imply total brackets, okay? So let's take a look at some examples. The first two examples are the first type where we're talking about ext. We talked about these Massey products last time. There's an element C0. We'll look at a chart in a minute just to illustrate it. There is an element C0 in the in ext, and it satisfies this. It equals this fourfold Massey product, h1 squared, comma h0, comma h1, comma h2, and there is another one, and there's also a threefold Massey product for C0, h1, comma h0, comma h2 squared. Okay, so what that says when you convert to stable homotopy groups, and generally we use Greek letters for the actual stable homotopy limits, stable homotopy elements, Latin letters for the elements in an ext or an E infinity, but then Greek elements when we switch over to homotopy is, so h1 squared corresponds to eta squared, h naught corresponds to 2, h1 corresponds to eta, and h2 corresponds to nu. So that's the corresponding total bracket. And what we're saying is that it is equal to epsilon, and epsilon is the name that for the element that C0 detects. Okay, and there, by the way, there is no consistent scheme for how Greek letters correspond to Latin letters. It's just kind of an arbitrary choices, and they got carried forward. It's historical artifact. Okay, don't look for a pattern there. Okay, and then similarly, h1, comma h0, comma h2 squared, that corresponds to eta, comma 2, comma nu squared. And notice how I've written that epsilon is an element of that bracket. The eta multiples and the nu squared multiples are the indeterminacy. And it turns out that there is an eta multiple in pi. So this is all happening in pi 8. And there's an eta multiple in pi 8. And so that eta sigma is the indeterminacy. Okay, well, again, we'll look at this chart in a second. Okay, and then the third example here is the other kind of example. Okay, so what you have, so here is a Massey product that you can form in E3, the homology of E2. So the differential now is the Adams D2. There's an Adams D2 here. Oh, sorry. Is H4. D2 of H4 is H naught H3 squared. H1 H0 is already 0. So those are the elements that have the correct boundaries. And then you have H1 times H4 plus 0 times H3 squared. That's the, so you have H1 H4 equals this Massey product in the E3 page. And what that means is that, again, H1 H naught H3 squared, that's eta 2 sigma squared. So this total bracket contains an element that was called eta 4, and the definition of eta 4 is something detected by H1 H4. Okay, so the point here is that this total bracket is detected by H1 H4, and again, there is some indeterminacy that's detected by PC0. Okay, so now let's go and let's just look at C0 and epsilon and eta 4 with the indeterminacy on an Adams chart, just to see it in practice. So we want the infinity page, and we're way up here near the beginning. Okay, so here is C0, and C0 detects an element in pi 8, in dimension 8. There's another dot here in pi 8, and that dot detects two elements of pi 8 that differ by epsilon. Okay, so here's epsilon. Here, we should write this. Here's epsilon. And then here, this dot is two elements. There's eta sigma, and there's eta sigma plus epsilon. Both of those elements of pi 8 are detected by that bottom dot. Okay, so, but eta sigma is kind of the natural. If you have to choose one, eta sigma is a good choice because it's decomposable. It's a product, but that's not, so anyway, so when we take that, there was one total bracket in which the eta multiples were the indeterminacy, and then there is an eta multiple here in pi 8, and so that's part of the indeterminacy. So that's what's going on there. Notice eta sigma is in lower filtration than epsilon. The indeterminacy can mess up the filtration. We're in the stable homotopy groups here, but kind of the filtrations have kind of gotten absorbed now, and so that could be all over the place. Okay? And then the other one was right here. There was H1, H4. There's notice in pi 16, there's 2 dots. There's PC0. PC0 detects a well-defined element. H1, H4 detects 2 elements. Those 2 elements differ by PC0. Okay, and that's exactly what happened. The Toda bracket had eta multiples in the indeterminacy, and see there's a hidden extension here. PC0 in E infinity, PC0 doesn't look like an eta multiple, but turns out it actually is an eta multiple, and so that puts PC0 into the indeterminacy. In other words, that bracket eta comma 2 comma sigma squared, it detects 2 elements. Those 2 elements it contains 2 elements. Those 2 elements are precisely the 2 elements that are detected by H1, H4. Okay, so in this case, the indeterminacy is in higher filtration and it works a little better. Doesn't have to be, the indeterminacy does not have to be in higher filtration, but and we saw that here, it wasn't. With epsilon, it was not, but with this eta 4, it is in higher filtration. Okay, so there's a lot you can do with Toda brackets. You can use them to understand, all kinds of hidden extensions and relations in the same way that the Massey products are useful for analyzing the May differentials. The Toda brackets and the Adams differentials, they play off against each other. So the analysis of Toda brackets is really essential for computing differentials in practice. And we won't have time to get into too much of that in today or the rest of this mini course. Okay, so now I want to go back and I want to go up here. Okay, so what I want to talk about with the rest of my time today is I want to show you one way to compute the V1 periodic stable homotopy groups. So if you look at an Adams chart, I'm going to zoom out intentionally. What you see, you just by inspection on an E infinity page, you immediately see some structure. What you see is this kind of regular or pseudo regular pattern up along the top, and then an ever widening gap, and then a bunch of noisy stuff down below. Okay, and when I go down here, and this is from the range 62 to 90, so and further out, this is the noisy stuff. I cut off the chart because it didn't fit so cleanly on the screen, so you're not even seeing the regular pattern. But what happens is that this regular pattern continues up to infinity, and this gap widens. And you can just see that from inspection. Clearly, there's something happening here. And this part at the top is what's called the V1 periodic homotopy. If you want to pursue chromatic homotopy theory and BP and the Adams-Novikov spectral sequence, you can define V1 periodic homotopy intrinsically, and you can compute it. But I don't want to do that. I just want to say, look, there's some homotopy up here, and let's see if we can compute it. Okay, first of all, let's look a little more closely at what the pattern actually is. Okay, so this part, this little upside down check, that's strictly periodic. Okay, every 8 stems, you get the same exact picture. Okay, and then you also have these other checks every 8, but they're a little bit different each time. The difference has to do with the height of the vertical lines. So the order of the group here is a little different than the order of the group here is a little different than the order of the group here. Okay, and inspection, if you looked at the chart, you may or may not be able to see the pattern. Okay, you probably, if you go all the way back to the beginning, start here and here and here, you can see a pattern that fits together. Okay, so that's what I want to do. I want to make a computation in which this pattern is spit out. This V1 periodic pattern is the result. Okay, that's the goal for today. So to illustrate these techniques and these ideas. Okay, there are many different ways of computing V1 periodic homotopy. Other people might have other preferred approaches. The different approaches highlight the different parts of the structure. The approach that I've chosen is the way that I like to think about it, because it fits in with all the other things that I tend to think about, and is related to a project that I happen to be working on recently. And so it's in the top of my head, but it's not necessarily the only way to do it. And it's not depending on your purposes, your reason for studying, your reasons for studying V1 periodic homotopy, it might not even be the best way. Okay, so let's do a little bit of, so let's get started here. Okay, so first of all, where all these atom spectral sequence ideas start with is the dual Stingray algebra. Okay, A star. It is a polynomial algebra on these zetas. Okay, and what I'm just saying is that the homology of the Eilenberg-MacLane spectrum is this polynomial algebra on zeta i's. Okay, now there is a co-fiber sequence here, Hz multiplied by 2 to Hz, and the co-fiber is HF2 for Eilenberg-MacLane spectrum. Okay, and what that means, I've drawn this double arrow here, and I mean implies, but there's some series of algebraic steps, but it turns out it's not that hard. This is really all you need. All you need is this co-fiber sequence and some algebra. And what comes out is a computation of the homology of Hz. Okay, so what you've lost here is zeta 1, the difference between the homology of Hz and the homology of HF2. HF2 has a zeta 1 generator, but H star of Hz only has zeta 1 squared as a generator, and zeta 1 is missing. Okay, and the reason that zeta 1 ends up missing here, essentially, and you go through the algebra, is that zeta 1 is dual to square 1, and square 1 corresponds to 2, or is the Bachstein. It corresponds to 2 in the sense that it's the Bachstein. Okay, but again, I know I'm skipping some steps here. I'm telling you, but this is an interesting argument that more people should be aware of, and you can go and read about it sometime if you want to know more about it. Okay, now little ku is complex, is connective complex K theory, and there's a map from Ku to itself called V1, whose co-fiber is Hz. Okay, the thing that we just computed up here, Hz. Okay, and from this co-fiber sequence and the computation of H star of Hz, you can do some algebraic manipulation, and you can compute the homology of Ku, little ku. Okay, and now what's happening is you've got this zeta 1 squared. That's already from the homology of Hz, but you're also losing zeta 2 now. Okay, zeta 2 drops out of the picture, and you have zeta 2 squared as a generator instead. Okay, and that is related to the fact that why is it zeta 2? Zeta 2 is dual to this Q1, this Milnor Q1 element, which is square 1, square 2, square 2, square 1, and that guy has some connection back here to this V1. Okay, so Ku, so you have the homology of Ku. And then there's real connective K theory, little ko. And little ko fits inside of a co-fiber sequence like this, where you have eta as the map, and then the co-fiber is Ku. Okay? That turns out to be what happened. That's not an obvious fact, but that turns out to be that's what happens. And again, this co-fiber sequence and a little bit of algebra gives you a computation of the homology of Ko. And what happens now is you had zeta 1 squared in the homology of Ku, but you lose the zeta 1 squared, and you have zeta 1 to the 4th as a generator. Okay, and that's real. And again, that's that this is all connected by the fact that zeta 1 squared is dual to square 2, and square 2 corresponds to eta somehow. Okay, all right. So what I'm sort of sketching here is a way that you can compute the homology of little ko. Okay, and you get that thing. All right, now when you could, so let's say we want to study the atom spectral sequence for little ko. All right, so you write down the inputs, the atom spectral sequence, and you stare at the ext groups that are the E2 page of this atom spectral sequence. And you can use the fact that the homology of ko looks like this. And you can end up rewriting the X groups in this way. Okay? The X groups turn out to actually be pretty simple to describe for little ko. From the perspective of the atom spectral sequence, little ko is a really useful spectrum because its atom spectral sequence is easy to describe. What you have to do is take X over some ring called A of 1. Okay? And A of 1 is defined, or its dual is defined by this quotient over here. And notice that there's the connection here. You see the zeta 1 to the 4th, the zeta 2 squared, the zeta 3. Well, that's exactly what you're modding out by over here. And that's not a coincidence. That's what happens when you go through when you go through and write down the X groups and do some change of rings isomorphisms is what it's called. What you find is that you need to work over this over this. You can do X over this A of 1. Okay, so what I'm not going to do is carry out the atom spectral sequence. Okay, because that's in the exercises. Right, so I've given you sort of step by step how to go through, how to carry out this computation, and how to get the homotopy of ko. I'm just going to show you the answer. Okay, this is what happens. Okay, you have down here, there's the identity element. You have this tower of H naughts, which we've seen before for the sphere, and then there's eta squared. Okay? But eta cubed is killed, and then in pi 4. You have another copy of Z. All these two multiplications assemble into a copy of Z. And then nothing for a while, and then pi 8 is another copy of Z, and then it repeats. It's exactly the same. This is exactly the same as that. That turns out to be what happens. And if you know, well, if you've memorized what the homotopy groups of ko are, it's sort of a familiar pattern. There's the Z2, there's the Z2, there's a 0, there's a Z, there's a 0, 0, 0, Z, and there's the repeating 8 periodic pattern from ko that maybe you're familiar with. Okay, so now the way I think about these things is I'm always, whether I'm showing it to you or not, I am always implicitly thinking about the C-motivic versions of these computations, because that's kind of that's what I live and breathe. That's just how I do these things. Okay, and in the case of this little ko, there's not too much to say. So we haven't talked much about motivic techniques in this course, and this is the one place where I'm going to say a little bit about it to give you a feel for it. Okay, so what happens? So here's what the C-motivic atom spectral sequence looks like. Okay, so there are two. You should compare to what I've got up here. There's two changes. First of all, F2 has been replaced by a graded polynomial ring, F2 adjoint tau. Okay, and A of 1 has been replaced by C-motivic A of 1. Okay, so and then C-motivic A of 1 I've described here. Now you have to read this formula, and you have to kind of compare it to this formula. And when you do that, what you'll see is that tau 0 sort of corresponds to zeta 1. And tau 1 corresponds to zeta 2. And C1 down on the bottom, that really corresponds to zeta 1 squared. The reason I say that is because you look at this relation right here. See, when you, it's tau 0 squared is tau C1. So tau 0 squared is almost equal to C1. And that's corresponding to the fact that zeta 1 squared is zeta 1 times itself. Okay, so that's the kind of the analogy that you have to think about. Now, if you carry out the computation of this C-motivic thing, then what you get is a very similar picture. You can see the classical picture here, and you can see the C-motivic picture down here. So it mostly looks the same, except there are a couple of things here that look a little bit different. And what happens is that here, H1 cubed, it would be sitting right there, but H1 cubed is hit by a May differential. That's not quite what happens here. H1 cubed is not hit by differential. It's tau times H1 cubed that is actually hit by the differential. And consequently, you have this copy of F2 adjoint tau modulo tau left over. That's what the red dot indicates. So it's just a copy of F2. The black dots are copies of F2 adjoint tau, but the red dot is just a copy of F2 adjoint tau mod tau. Okay, and you get these infinite multiple H1 towers here, and the same thing will happen on all these other H1 towers. The first two stages are the same as before, and the third stage becomes this little tau torsion, this tau torsion guy, and those tau torsion sequence of tau torsion elements. Okay, so there's a specific reason why I've taken this digression and told you about the C-motivic version of the computation for KO. Okay, and that's written at the bottom of the screen. Okay, if I want to know the classical Adams-Novikov spectral sequence for little KO, I can either do some computations involving the Brown-Peterson spectrum BP, and maybe do some chromatic techniques or this or that or whatever. I could try to compute it directly the way that the BP star people or the chromatic people would tell us to compute it, and that's a fine way of finding the Adams-Novikov spectral sequence for KO. Okay, but I have a different way. The way I find the Adams-Novikov spectral sequence for KO is that I can reconstruct it from the C-motivic Adams spectral sequence for KO. Okay, so the point is that if I look, instead of looking at C-motivic KO, I could consider C-motivic KO mod tau. And if I consider C-motivic KO mod tau, then this co-fiber sequence will give me a long exact sequence in X groups that'll look something like this. Okay, so you'll have the kernel of tau on one side, the co-kernel of tau on the other side, and they'll assemble into a copy of C-motivic X for KO mod tau. Okay? And this is the picture that results. When you carry out that, this is the picture that results. When you look at the co-kernel of tau, that's just a copy of all of this stuff. All of this stuff, when you mod it by tau, it's all of this black stuff here. Okay? The kernel of tau is just this stuff here. That's the only thing that tau annihilates. Okay, and then that stuff shows up here. Okay, so you have the black things from the co-kernel, you have the red things from the kernel, and then there's a little hidden extension. See, there's this short exec sequence, but it turns out that there's an extension there, and that's indicated by that blue line. Okay, so this is the Adams E-infinity page for KO mod tau. This picture is exactly the same as the Adams-Novikov spectral sequence for KO up to regrading. There's a theorem that says that when you're working C-motivically mod tau, what you're really doing is classical Adams-Novikov. That's roughly speaking I mean, that's not the way the theorem is stated. That's not so precise, but that's what in practice, that's what the theorem is telling you, is that you can work mod tau and you can get all this Adams-Novikov information. Okay. So when you do that, and you have to know how to translate, and we're not going to get into all of those details, but when you know how to translate, here's what happens. Okay. There's this tower here, which corresponds to a Z, and that assembles into a Z right there in the lower left corner. And then there are this infinite tower of H1 multiples, and that gives you this infinite tower of H1 multiples. Okay. Next, you have this infinite tower, which corresponds to a Z in the 4-stem, and you have its H1 multiples, which corresponds to those H1 multiples. Okay, and then the process repeats. That there's this stuff is corresponding here, and so forth. Okay, one thing that you might be a little bit puzzled by is why did this dot, which was, look, it's up here in filtration 2, this dot in filtration 2 got shifted all the way down to filtration 0. Okay, and that's exactly, like, if you're wondering about that, then you are absolutely wondering about, that's exactly the right question. You should be wondering about that. And that's the way the theorem works. That's when I say that the Adams-Novikov can be reconstructed. Part of that process is reindexing. Okay, and then this element ends up getting shifted down to filtration 0. In fact, all of these guys are all in filtration 0. Okay, now there are also so this is what the E2 page for the Adams-Novikov spectral sequence for KO looks like. And there are differentials in this spectral sequence that can also be read off of the motific information. Okay, so it's not new information. It's really the same. Well, I guess maybe you need to go all the way back here. But anyway, this motific information tells you about the presence of all of these differentials. All right, well, let's look at what happens with these differentials. So there's a copy of Z here, and there's a copy of Z mod 2 here. Okay, so the Z maps onto the Z mod 2. So the Z mod 2 is wiped out. But notice that 2V1 squared survives. V1 squared hits H1 cubed, but 2V1 squared maps to 0. 2V1 squared is a cycle. Okay, so so you have these 3 dots that carry over to E infinity. You have 2V1 squared, which carries over. And you have these 3 things that carry over, and then 2V1 to the 6th, and so forth, right? And then it continues off to the right periodically. Okay, so that's what the Adams-Novikov E infinity page for little KO looks like. Okay, it's not too bad. It's well understood. We got a complete handle on it. Okay, and then again, you can see the Z2, the Z2, the 0, the Z, the 0, 0, 0, Z, and so forth. Although really notice what you're seeing here, it's not so much Z as it is 2Z. Obviously 2Z is isomorphic to Z as abstract abelian groups, but it's really better to, in many ways, it's better to think about this pi 4 as being a copy of 2Z rather than a copy of Z itself, but that's a side point. Okay, now I need some geometric input, okay? So that's sort of like the dirty little secret of all these kind of algebraic style of computations in stable homotopy theory, is that sooner or later, you have to do some kind of geometric input. The stable homotopy category is topological. It does carry topological geometric information. You can't deduce, you can't necessarily deduce everything out of thin air. At some point, you have to have some geometric input. Okay, and here's the geometric input, and I've been very careful here. This is the one place in this talk I've very carefully kind of put this geometric input into a black box, and this is the only geometric input that you need. Okay, so there are Adams operations on K theory, and that's what psi3 is. Psi3 is an Adams operation, and it comes from the fact that vector spaces have exterior powers, and you study the third exterior power, and then you soup it up to vector bundles, and you use the fact that KO has some relationship to vector bundles, and you end up with a map psi3 from little KO to itself. Okay, but you actually study psi3 minus 1. Right, psi3 minus 1 has an understandable effect on the homotopy groups of KO. Okay, so in dimensions 4K, it is a copy of Z. That's all these Z's here that we see. Dimension 4K, it's a copy of Z. Okay, so you have a map from Z to itself, and it is multiplication by this particular integer. Okay, that's the geometric input. That psi3 minus 1 is a self map of KO that has that effect on pi 4K. Okay. All right, so now what we're going to do is study this little j spectrum. Okay, so this it's little j. That's its standard name. I've actually written j prime. Okay, so normally what you do is you change the target a little bit, and then you let j be the fiber of the map from KO to a slightly different spectrum. Okay, I'm going to ignore that complication for expository reasons. I'm just going to leave it as KO. But then what I'm going to get is a spectrum, as its fiber is a spectrum that's a little different than what most people would call little j. And so I'm going to call it little j prime, because I don't want to confuse you. So I'm doing something a little different, but computationally, it's just as good. So there's not really any harm in making that simplification. Okay, so you get a fiber sequence here. And that fiber sequence will give you a long exact sequence of Adams-Novikov E2 pages. We've already discussed the Adams-Novikov E2 page for KO and the Adams-Novikov E2 page for KO. And since we know 2 out of the 3 Adams-Novikov E2 pages, we can figure out the Adams-Novikov E2 page from the long exact sequence, okay, in the usual way. We've got to have the kernel of psi 3 minus 1 and the co-kernel of psi 3 minus 1 with a shift, because there's always this shift when you look at these cofiber, these long exact sequences. Okay. And then we've got to figure out what the co-kernel and the kernel actually are. Okay, so let me tell you what the right. So the point is that psi 3 minus 1, when you work, in degree 4k, psi 3 minus 1 is multiplication by this integer. You have z to z multiplied by that. And so you're going to get z mod something. Now, what you might have expected to see here was 3 to the 2k minus 1, z mod 3 to the 2k minus 1. But here's the thing. We've been working sort of, at the prime 2 through all this whole mini course. And in particular, when I write z, what I really mean is the 2 adic integers, because I'm working 2 complete everywhere. And in the 2 adic integers, odd numbers are units. So I don't really, when I'm taking this quotient group, I can ignore them. I don't really need them. All I need is the 2 primary parts of 3 to the 2k minus 1. Okay, and so that's, I've got z mod 2 to the z mod the 2 primary part, and then the 2 primary part, there's a very easy number theoretic exercise. I put it into the I put it on the exercise sheet. It's not you just basically just factor this thing using sort of like obvious tricks. And here's the pattern of numbers that comes out, the 2 adic valuation of 3 to the 2k minus 1. Here are the numbers you get. You get 3, 4, 3, 5, 3, 4, 3, 6, 3, 4, 3, 5, and so forth. Okay, and here I've drawn it kind of geometrically. Okay, so here's the 3, 4, 3, 5, 3, 4, 3, 6, 3, 4, 3, 5, 3, 4, 3, 7. Okay, so there's kind of this binary kind of recursive pattern here. Sometimes we call this a ruler pattern, right? This is the way the marks on a ruler, or at least not a metric ruler, but the marks on a English system ruler would look, right? You have 1/16 of an inch are short marks, and then 1/8 of an inch are longer, and then 1/4 inches are a little longer, and the 1/2 inches are a little longer, and so forth. And you end up with a pattern like this. This is a pattern that all stable homotopy theorists should be familiar with. This type of pattern occurs again and again and again throughout stable homotopy theory in many different places. And you should be ready to see this pattern when it occurs and recognize it for the pattern that it is, and then connect to things like the V1 periodic homotopy and image of J and so forth. Okay, so as stable homotopy theorists, we should all be on the lookout for these types and their variations. Okay. All right, so let's go. So what we need to do is we need to analyze the co-kernel of psi 3 minus 1 and the kernel of psi 3 minus 1. And so that's what I've tried to draw in this picture that you see in the middle of the screen. I've tried to do this kind of carefully. Okay, so, and I've taken the long exact sequence and I've written it vertically instead. Okay, so here's E2 of KO at this height, and here's the second copy of E2 KO at that height, and there's the psi 3 minus 1. And I've written in red, I've labeled what the map does. Okay, on the Z's, that's what it does, and on all the Z mod 2s, it's 0. I haven't written that in, but it's 0 on all of these Z mod 2s, and that's not hard. That follows from the other stuff. That's not a hard fact. Okay, so when you want to take the kernel and the co-kernel of this map, okay, well, the kernel I've drawn up here in green. Okay, notice it's basically the same, except you get rid of these guys, these Z's, because these Z's support multiplications. But everything else is the same as before. So there's the kernel. And then the co-kernel, mod up by the image of these maps. And instead of a Z, what you get is a Z mod 8 or Z mod 2 to the 3. And that's what a box means. A box with a number in it means Z mod 2 to that number. Okay, so that's Z mod 8, that's Z mod 16, that's Z mod 8, that's Z mod 32, that's Z mod 8, and so forth. And there's those patterns 3, 4, 3, 5, 3, 4, 3, 6, and so forth. That's this list of numbers that goes along that. Okay, so there's the kernel, and there's the co-kernel. Now what we have to do is take this kernel and this co-kernel, and we're supposed to assemble them together to get E2 of J prime. Remember, here is this short exact sequence. A co-kernel and a kernel assemble into an E2 of J prime. And here at the bottom of the screen, you can see the result of that. Okay, the kernel is corresponding down here to the black elements. There's and I've given them their names that came from the names that we used in E2 of KO. Okay, so the black ones are from the kernel, and the red ones are from the co-kernel. And there's a shift. And you'll see that that they don't quite line up anymore. They're shifted over here to the up and to the left, and that comes from this shift here. When you go through the indexing carefully, you get a shift. Okay, so this is a picture for the Adams-Novikov E2 page for J prime. And J is the actual J, the usual J, is very similar to this, but it just got some slightly non-periodic patterns to it that are just kind of annoying to deal with. Okay, now I've given names to these elements, and the names in black are coming directly. It's a kernel, it's a sub-object of E2 of KO. The black names are coming exactly from E2 of KO. The red names are also coming from E2 of KO. What they mean is they're recording the values of this map. When I call this one V1 squared bar, what that means is that it is the image of V1 squared under this map. And this one is called V1 to the 4th bar. It is the image of V1 to the 4th under this map to the co-kernel. Okay, so so the names here are keeping track of how the kernel and the co-kernel kind of came from little ko. Okay, I've also written in green, I've also written a different set of names. Okay, you may have heard of people talk about the alpha family, or you may have studied the alpha family, may have computed with it in the Adams-Novikov spectral sequence. Someone who comes at this from a more chromatic perspective would not call these elements H1, V1 squared, and V1 squared bar. Such a person, a chromatic person, would call these alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7. Okay, and because there's another way of computing this, and from that perspective, they fit into a family. But from my perspective, there isn't really one family. There are really two separate families. There's the family that came from the kernel, the ones in black, and there's the family that came from the co-kernel, the ones in red. And it's really kind of important to separate them. In order to understand what's going on, you really kind of want to separate them. Okay, so there's the Adams-Novikov E2 page for J prime. And then the next thing is to look at Adams-Novikov differentials. And it turns out there are some differentials, and I've shown them here in blue. Okay. These are corresponding completely to the differentials that we saw for KO. When we go way back up here, we saw a couple of D3s for KO. And you take those differentials for KO, and you apply what they imply here is precisely, there's really sort of two families of differentials. There's one family of differentials that go from black elements to black elements. They're here and here. And then there's a second family of differentials that go from red elements to red elements. So there's here, and there's another family. There's another sequence here. And notice that all of these guys, they're all actually an H1 periodic family. There's actually an infinite ladder of differentials, and this is an infinite ladder of differentials, and this is an infinite ladder of differentials, and this is an infinite ladder of differentials, and so forth. Okay, so that just comes from little ko. There's not really much new going on there. And then finally, from here, you can get to the E-infinity page, the Adams-Novikov E-infinity page for J prime. Okay, so these first three red elements, they survive. They're sitting right there. That's fine. Then there's these four black elements, and they're sitting right here. And now look a little carefully at what's going on here. You started with a Z mod 8. It maps to a Z mod 2. But that means that there's a Z mod 4 that survives, that's in the kernel of this map. And so there's a Z mod 4 that survives. And notice it's 2 times, here you have V1 squared bar, here you have 2 V1 squared bar because that's the Z mod 8 to Z mod 2, it's twice the generator is in the kernel, right? Okay, all of these thing is all gone because it supports differentials. And then you go on to the next part of the pattern, you have these 3 that are these 3, and then you have these 3 that are these 3, and then this guy is a Z mod 8 again, but only a Z mod 4 survives, and so forth. And the pattern repeats. Okay, so there's some of the red dots survive, some of the black dots survive in this pattern. Okay, now there's another thing that you see in this picture. In addition to the E-infinity page that I just computed, there's another phenomenon that you see, and that's these hidden extensions. These are hidden 2 extensions, exactly in the sense that we talked about in the first lecture. There is this E-infinity page, this Adams-Novikov E-infinity page for J prime is not, we're not looking at the homotopy groups of J prime, we're looking at an associated graded for the homotopy groups of J prime. Okay, and then you have to sort out the extensions, just as we've talked about it, in detail in the first lecture and in the first problem set. Okay, and what I'm telling you when I draw these curved lines, what I'm telling you is that there are hidden extensions. That this group here, this pi 3, is not Z mod 4 plus Z mod 2. Rather, this pi 3 is actually a Z mod 8. And then the same thing happens out here. This pi 11 is not Z mod 4 plus Z mod 2. It's actually a Z mod 8, and so on and so forth. Okay, so then the question becomes, well, how do you get these? How do you know that those hidden extensions are there? Okay, so let me tell you one way to get those. Okay, and this is kind of a useful theorem to know about in itself. Okay, so the theorem is, let's take X could be any spectrum, any stable homotopy object at all. Okay, and suppose you've got some homotopy element in that you're studying the homotopy groups of X. X could be the sphere spectrum, X could be J prime, X could be KO, X could be TMA, X could be, it doesn't matter. Okay, doesn't even have to be a ring spectrum, it could just be anything. Okay, then one of 2 things happens to alpha. It could be that 2 alpha is non-zero. That's one thing. Okay, and then in the other case, 2 alpha is 0. Okay, when 2 alpha is 0, then alpha times eta squared has to be divisible by 2. Okay, and of course both could occur. Right, it's not an either or. Okay, so there's actually sort of an understandable proof here that we can write down. Just takes a few lines. Okay, so X is an S module, and what that means is that pi star of X, the stable homotopy groups of any spectrum are what I call a tautomodule over pi star of S. Tautomodule is not a standard terminology. There isn't standard terminology for the structure that pi star X has. So I call it a tautomodule, and I put it in quotes because I don't have a precise definition for tautomodule. But what I mean here is that you can form tauta brackets of this form alpha comma beta comma gamma, where alpha comes from X, but beta and gamma come from S. And so this is sort of like an action, right? When you, like a module action where you have, M is an R module, you have R dot M where R is in the ring and M is in the module. And that's kind of what's happening here. Alpha is in the module and then beta and gamma are like in the ring. And notice, so it's like a right action, the way I've written it, okay? But it's not true for any alpha, beta, and gamma. You need to have these conditions that alpha beta is 0 and beta gamma is 0. When alpha beta is 0 and beta gamma is 0, then you can get this kind of a construction in pi star of X. Okay, so if 2 alpha is 0, 2 alpha is non-zero, or 2 alpha is 0, if 2 alpha is 0, then when you look at alpha eta squared, you can write it as alpha 2 eta 2. And that's actually a bracket. Eta squared is 2 eta 2. That's, well, we talked about the Massey product. We talked about h1 squared is h naught, h1, h naught. But that's the same as the total bracket. Eta squared is 2 eta 2. So here all I've done is replaced eta squared with 2 eta 2. And then you apply a shuffle relation. We talked about shuffle relations for Massey products last time. The same types of relations hold for total brackets. And when you shuffle, so you have 4 elements here, and shuffle the brackets to the left, and you get this last expression. And there it is. Alpha times eta squared is a multiple of 2. Okay, so this is actually a really interesting sort of non-obvious result. You know, here's a question that would occur sort of inevitably in stable homotypic theory. Suppose you are given some algebraic thing, and you are asked, could this algebraic object be the homotopy groups of some spectrum? That's a reasonable question to ask. It's the sort of thing that comes up. Okay, so and well, first of all, so it had better be a module over pi star s. Module in the ordinary usual sense, pi star is an ordinary ring, and pi star x is an abelian group, and pi star x could have a module structure over pi star s. It better be a module over pi star s. Okay, so suppose it's a module over pi star s. Is that enough? Does every pi star s module arise as the homotopy groups of a spectrum? Okay. This theorem says no, they do not. Okay. If I were given a pi star s module and I was asked, are these the stable homotopy groups of the spectrum? The first thing I would look for is this algebraic condition. Are there any places where you have a 2 torsion element where you have 2 alpha is 0, but alpha times eta squared is not divisible by 2? That's what I would look for. Okay. And you know, this is a non-trivial restriction that is not implied by the pi star s module structure, by the ring structure. You have to do some kind of total bracket, some sort of slightly deeper thing in order to see this restriction. Okay, and the point for us is that this theorem immediately tells us that we have the 2 extension. Why is that? Well, here is an element in pi star of j prime. Okay, it is killed by 2. 2 times it is 0, and so therefore you take eta squared, that's here, and that eta squared must be divisible by 2. The only possibility is that there has to be a 2 extension. Okay, so that's a complete proof. And the same thing here. Here's an element, it's killed by 2, therefore eta squared times it is 2 divisible, and so forth. Okay, let's go, since we're talking about these guys, let's take a look at an eInfinity page again, just to see these kinds of relations. So, you know, here's a good example. Let's take a look at this part of the stable homotopy groups. Okay, so we're in the 40s here, high 40s here. Okay, so suppose you've already figured out these eta extensions. Suppose you already know there are these 2 eta extensions here. Okay, and now you're asking yourself, is there a 2 extension here? Well, the answer, again, same as before, the logic is the same. Here is an element that's killed by 2, therefore eta squared times it must be 2 divisible, and there has to be a 2 extension here. Okay, so these eta extensions imply this 2 extension. Okay, so there's these tight connections between things. You know, in this range, maybe I know them for other reasons, but if you go far enough out, some of the 2 extensions in the, oh, here's a good one. There's one that I think I don't have another proof for. I think the proof of this 2 extension here really is this theorem that I'm talking about. You start with this class, and that's theta 5, by the way. That's the Curvaire class, theta 5. Theta 5 is killed by 2. Therefore, theta 5 eta squared is 2 divisible. Okay, and there's a proof for this hidden 2 extension. Okay, so these things occur. Here's another one that's related that way. Here's another one that's related that way. Notice this one, you've got the 2 extension, it's primary, right? The two divisibility isn't hidden and so forth. Okay, so this is actually a useful. This one is interesting here. Here are 2 eta multiplications. It turns out that this guy cannot be 2 divisible. It's not possible. I mean, you can look at the dots, but you can argue them one by one. turns out that that one's not 2 divisible. Therefore, this guy can't be killed by 2, and in fact, that gives you a 2 extension on the start of the eta squared multiple. Okay, so there's different ways that you can use this thing, and it gives you not already this very kind of elementary theorem already gives you lots of non-trivial results about hidden extensions. Doesn't tell you everything, but it tells you a bunch. Okay, let's go back here. All right, so this gives you so here you are, you're done, you've computed the homotopy of J prime, and the homotopy of J prime is closely related to this V1 periodic homotopy. Here you see the 3, but notice it's actually a hidden extension. It's 2, there's the 2 to the 3rd, then 2 to the 4th, then 2 to the 3rd, then there'll be a 2 to the 5th, and so on and so forth. And you'll see that pattern, that 3, 4, 3, 5, 3, 4, 3, 6 pattern that we talked about earlier that we were looking for. Okay, so again, the real point of having gone through this Adams-Novikov E infinity page for J prime is to sort of like to illustrate the kinds of, how these techniques get used to carry out an actual sort of, natural computation. Okay? And then the one last remark I'll make has to do with this business about J prime versus J. The real definition, the usual definition of J, it's the cofiber, it's the fiber of a slightly different map whose value is sigma 4 KSP. And the only difference between J and J prime is this stuff right here. Okay, so this stuff is in J prime, is in the homotopy of J prime, but it is not in the homotopy of J. And in a sense, it doesn't, those 3 elements don't really belong. The rest of these elements correspond to actual elements in the stable homotopy groups of the sphere spectrum, and these first 3 don't really correspond to something from the sphere spectrum, and so you might feel like they don't belong. However, in some ways, it really makes the pattern more regular to have them in there, and so that's why from my perspective, I don't really care about the -1 stem, the 0 stem, and the 1s. I already know the -1 stem and the 0 stem and the 1 stem, so putting these in doesn't confuse me. I just have to account for it. Sort of low dimensions behave a little different, and I can account for that easily enough. Okay, so this is where I'm going to stop the lectures for the mini course. But of course, the activities will continue on Thursday. We'll meet for a problem session, and then next Tuesday, 1 week from today, we'll meet for the 3rd problem session. Thanks, everyone.
Okay. Let's first thanks Dan for the great talk. So you can either like unmute yourself or you can use a reaction. And now we will open up for questions if there are any.
Good question.
Yeah.
So when you were applying this theorem and showing the charts, it looked like sometimes there were multiple classes in lower filtration. So how do you know which one is supporting that hidden 2 extension?
Right. So you don't. But it's the you have to look at all the possibilities, and you can eliminate it as soon as you eliminate all but one possibility, then it's the last one, right? It's the Sherlock Holmes approach,
I see,
so to speak. So yeah, there's nothing you can do about it. They could be different lengths. They're not always extensions of a given length or anything like that. I mean, well, okay. There actually. Let me take that back. There's something that you can actually do. You see, look, this theorem is actually a little bit better than what it stated. It's not merely that alpha eta squared is divisible by 2, but it's actually giving you a total bracket for the thing whose 2 multiple is alpha eta squared. So if you have some way of computing alpha 2 eta, then you can actually figure out the source of the 2 extension.
I see. Thanks.
Sometimes you do have a way of figuring out alpha 2 eta, and sometimes you don't. Here, let me show you one. That's a good question, because now I'm realizing. So here, see here, H1, H6 is H1, H0, H5 squared, and that's in E3 because D2 of H6 is H on H5 squared. And so therefore you have a total bracket, right? So H1, H6 is detecting the total bracket eta 2 theta 5. And so, and there it is, right? That's, you know, I mean, you already knew it in this case because there was only one dot down there, but it's just, I'm just pointing out that's the thing that's supposed to be. So then what we're shuffling is 2 times eta 2 theta 5 equals 2 eta 2 theta 5 equals eta squared theta 5. Okay, so that's sort of illustrating it. I mean, again, in this case, your question didn't pertain to this case because of course it's that one. What else could it be? But some, you know, in some of these other ones, you might be able to do something like that. It depends on the specific situation, the specific alpha.
Thanks.
Any other questions?
Hi, Dan. I'm wondering if I can ask about the massive product that's really like the topic of the last lecture. Is that
Sure.
appropriate? Yeah. So like basically in the exercises, like you asked us to check that there's a full four-fold massive product that defines the element H sub 0 parenthesis 1. So I remember like in the lecture that you said like in order to define a four-fold massive product, like you need say you need both the threefold sub massive product to vanish. But there was also like the Adams theorem you mentioned that like the total the massive product H is that H12 H23 H12 is equal to H23 squared. So I was wondering if there's a contradiction there, or am I just messing up the products on different pages?
Yeah. So right. I think I know what you're talking about. So Adams's theorem about massive products of the form Hn comma x comma Hn. Yeah. That theorem very specifically applies to massive products in Ext over the Steenrod algebra.
Okay.
That's where that one applies. Not in a general DGA. That is a very specifically related to the Steenrod, to the cohomology of the Steenrod algebra. Okay. In other DGAs, you wouldn't necessarily have that.
Oh, okay.
Okay. And then the one in the example is a different DGA. And so that's why it's turns out that what is it? H0 H what is it? H1 H2 H1 I think is the one. That one is it's 0 in that DGA in that example.
I see. Yeah, so that was different.
Yeah.
DGA.
Yeah.
Okay. Are there any more questions? Okay, if there's no more questions, maybe let's thank Dan again for the great talk. And also, like the quick reminder is like we will continue the activity and there will be exercise on Thursday.